Hello, I'm John Everest, and this is a simple presentation discussing where radiance is actually the surface area's radiance is sampling when it's calculating the diffuse light. Now, what I mean by this is when you make a calculation of a room and the light is bounced around, it's not like as unlike in the real world. It's not literally looking at every single photon of light that is hitting the surface. It is making controlled guesses based on probabilities of where it needs to make sampling, and it is interpolating in the bits in between. But the question is, where are those areas, and why is it choosing the areas it's going, and what control do you have over it? This is really simple. It's just I was just putting something together, and I thought maybe it's just worth throwing a 5-minute job. Um, let me show you Rhino here. So basically, I just made a it was for something else I was doing actually. I got on sidetracked actually because this is the second video I've done. But yeah, so here's a room. Yes, so the sunlight's going to come in and it's going to go through these blinds, and the light will enter the room and then it will bounce around. The way radiance works is, firstly, it actually calculates the light contribution separately. So it will first calculate the direct component of the light. Then it will calculate the diffuse light, that is the bounce light. So if you were to just run a calculation, there's our room, there's the windows and the blinds highlighted. If we were to just run a calculation without any with only direct light, this is what it would look like, and I think that makes sense. That can make sense to you, can't it? So if I just flash back to the room, so we're kind of standing here, the light is coming in through the window and it is making a pattern here, but we have not told Radiance to actually do anything more than that, just bring in the direct component of the light. It's a really fast calc. This calc will happen at a very high resolution. This calc will happen in a matter of seconds. In fact, it's the speed of it which is what makes the 5-phase daylight method so effective, because it can just quickly do these direct component calcs. Now, if we want it to actually look a little bit more realistic, we want to bounce some of the light around. It's a coarse render, and notice I've only used I think it's 3 light bounces, so there's a lot of darkening round here, but it doesn't matter. I just wanted a quick calc. So to actually bounce the light around, we have to tell Radiance to do something extra. The direct light has entered the space. Now, unlike the radiosity method, where I don't know if you've seen radiosity, where what happens is the model gets divided into like a mesh grid, and it's just lines of sight. Because this is ray tracing, it happens slightly differently. So what happens is Radiance starts to look around the space. When we're at this point, it starts to set up sampling points. In fact, can I even do this? It just starts to basically put sampling points across the surfaces, based on parameters that you give it. Yeah, so it just starts putting them around, and then what it starts doing is looking at what is the difference between this sampling point and that sampling point. If it's outside of a tolerance, it says, well, okay, now I need to put in another sampling point because there's a big difference there, and it will look at the difference between that, and it will say, okay, I need to put in another point. Okay, and what that starts to look like is this is literally the sampling points from the calculation I was making. What was actually happening was I'm so disorganized with all the images I generate. I was getting a funny pattern on the wall here, and I was trying to understand why it was happening. And so I just basically made this simple script that reinterrogates the Radiance file, and just brings all this data out. So what we can see here is it's just generally spreading these sampling points across the surface. And note, can you see how it's doing extra sampling points in the corners, in the crevices, and places like that? And if you think about it, the reason it's doing that is because there is a rapid change of brightness, isn't there? As you come out of the corner, in particular. As you start to pull out of this corner, then there's going to be a rapid change. So it's putting in lots and lots and lots of sampling points. And these red ones, that is just for the first bounce. So it looks around and it says, based on the first bounce of light, these are the sampling points, and I will, based on the specification I've entered, and I think I'll just cover that some other time on a different video, is whether that is adequate. My initial points are adequate, or do I need to add more? And in these areas here, it needs to add a lot more. Then it goes on to the second bounce, and it repeats exactly the same process, and it says, right now, based on the light energy stored across the surface, I'm going to look around, and again, I'm going to ask the question, do I need to set up additional sampling points and so forth? And once again, you're getting this clustering in the corners and the crevices of the room. And then it goes on to in this calculation, I only bothered to do 3. Goes on to the third one, and it does exactly the same again. So it's sort of building up this mesh of sorry, wrong term, this distribution of sampling points across the surfaces, based on like I say, based on the luminous variance across the surface and the specifications I give it. Which, if any listeners know the Radiance syntax, is the AB, AA, AR, AD, AS. It's based on those specifications. In actual fact, they're all relevant, but it's the ones that govern these distances are AA and AR. Okay, and in actual fact, it is the maximum. It's the max scene dimension divided by AR, and that will give you the kind of the starting point for the calculation, right? That's where it's going to sort of start to set out its sampling points and and then make its own calls. And then the other one is the max scene dimension divided by AR times AA, right? And what that actually dictates there, that one below, is the minimum, the minimum point, the minimum density of points it's allowed to get to before it just starts interpolating regardless of luminous variations. So should this equal, not that I'd ever do a calc like this, but should it ever equal 1 meter, it will never cluster these sampling points closer than a meter, which would mean you'd have a pretty coarse calc. Not sure. Well, actually, I would never do that, because it wouldn't be particularly accurate, would it? But well, maybe if that was a centimeter, perhaps that's more meaningful, isn't it? So, and the reason for that is so you don't, like, if you didn't have that figure in there, it would start obsessing over, like, I don't know, like a wire or something, because there's no limit to, all it sees is rapid changes, so it will start looking at those. So as you change these figures here. And really, I find AA, you want to leave that always at least 0.1, no higher than 0.1. AA should be, and control the rest with AR. That's the way I always do it. But so then as you change those, the sampling points change in their density, and you start to get a more accurate calc, and you start to lose some of the you'll start to lose some of the blotching. This is also a product of the ADAS function, but like I say, I just wanted the calc to run nice and quick. Yeah, and as you tighten those up, the calculation becomes more accurate. Less interpolation is happening, but there's a time cost, because of course from there to there is probably fourfold the calculation expense, and that's just for the first bounce, and exactly the same thing can happen for 3 bounces or 4 bounces or 5 bounces. But as I say, that's just to share some knowledge on when Radiance is doing that, or maybe you're getting strange results. It could be because this is how the sampling is working. Okay, I hope that's useful.